Yes, so I'm Pierre-Luc. I work at Xanadu downtown Toronto here. It's a quantum computing startup. And I'm a quantum physicist there. My job is to find applications for quantum computers. So that's my specialty. I'm less of a specialist in quantum machine learning, but like the maths are very similar to statistical physics. So we're looking at those types of algorithms for future quantum computers. I don't expect that there's much expertise here in quantum computing, so I'll try to be as pedagogical as I can. If you have questions, ask them, because like there's a language gap and it's very hard to bridge. So like there's at the core it's linear algebra, and yeah, if you have questions, ask them. I can try to like make it more clear on the whiteboard. Also, like I try to make the formalism as graphical as possible, but it may not be completely perfect. So what I'm going to talk about is quantum generative adversarial networks. The idea came about probably around March, and we developed it quickly. So it's a way to generalize generative adversarial networks as you have in machine learning to a regime where you can apply it to quantum computers. So quickly, I'm going to say a few words about Xanadu because they're paying me. Then we can say a few words. Then we can talk a bit about quantum computing, and then I'll move on to quantum generative adversarial networks, which we name QGANs. So about Xanadu, we're like a photonic-based quantum computing company close to Spadina and Richmond. We do like the full stack, as we say. So we build the hardware using photonics, the software layer also. So we're building like the interface to the quantum computer, and also packages like to do chemistry and machine learning on those systems, such that you never really have to code like the quantum computer. You're just like calling classical functions. It's sending it all the way back and forth, and then you don't really have to like see what's inside the machine. And yeah, we're like developing new algorithms. We're testing the chips, and hopefully we're gonna get like a small workable prototype very, very, very soon. Like we're backed by most major VCs in Canada, and up to now, like the first funding came in April 2017, and now we're like 25, almost 30, I think today. PhD student, like at least PhD in quantum information. So like it's just moving very, very, very fast. Yeah, so we're doing quantum computing. So the picture of quantum computing that I'm going to talk about is the picture like given in this, like it's the textbook of the field, so by Nielsen and Schwang. So this is like the canonical picture of quantum computing, but there's many difficulties and caveats. I can talk more about them like at the end if you're interested. It's the idea that like if we add the quantum computer like working, like how can we use it to define quantum adversarial networks? You've probably heard a bit about like the idea of a qubit. So like in the classical computers, you have zeros and ones. In quantum physics, the states are defined by what we call like a state vector. So and since quantum mechanics is linear, then we can also apply the superposition principle, and the states of matter at the microscopic level can be described by this continuous. So if you pick a system with two possible states, say a spin which can be up and down, then the state of the system can be described by a continuous vector on a sphere, which we call like a Bloch sphere. And this is really like the notion of a single qubit. So instead of having 0, 1, you can have a 0, a 1, and like everything in between, like on the surface of this sphere. And but when you measure the device, it always collapses. Well, in the computational, what we call the computational basis, it collapses to a 0 or 1. So when you observe it, it's always in a definite state. But when you're applying operation on it, it can be in a undefinite state, say around the equator, where it has a chance, say, of 50% of being 0 and a chance of 50% of being 1. And that's like the basic computational unit. So like when I refer to a channel or like something, it's like really like a qubit degree of freedom. So 0, 1, and everything in between. And it's called computers because we can apply gates. on it. The principle is that when we extend classical computing to reversible functions, then it's become easy to map it to quantum algorithms, because quantum mechanics is unitary. It means that you can reverse time and like it still works, you're not losing information. It means that your computations are reversible. It allows you to define a set of gates on these channels. There's there's the obvious, what we call the identity gate. So it means just you take a qubit and you do nothing on it. And there's a matrix representation also. Like this matrix representation tells you like state 0, 0 goes to 0, 0, state 1, 1 goes to 1, state 1 goes to 1, and like the in between, they don't move. There's the equivalent of the NOT gate. So like this one flips it. So if you have 0, it flips it to 1. If you have 1, it flips it to 0. And there's a more quantum-ish gate. Say like the equivalent, like the Y gate also does like X, but around another axis. So it's like a rotation around Y. X is like a rotation around X. Z is a rotation around like the center axis. And there's a bunch of other useful gates which are essentially like small rotations on that sphere. And coupled to basic like 2-qubit gates, like the control NOT. Control NOT, it means that if you have a 1, you're flipping the other bit. Swaps and other control unitaries, then you can build all functions in the quantum computer. This set of gates is called universal, in the sense that you can implement all algorithm with a polynomial number of these gates in the quantum circuit. And those algorithms, like the canonical known algorithms, there's what is called the quantum Fourier transform. So it's a way which is more efficient to do a Fourier transform on some data set. And from this, there's another more complicated algorithm where you use the Fourier transform. And if you have some state, say the state of an atom or a molecule, then the phase estimation is a way that your computer will output at the end here, like the energy of the state. So is like, what is the energy of this molecule? This guy will just tell you in a digital form the energy of that molecule. And classically, if you try to do that on a classical computer for all molecules in general, what you're going to get is an exponential amount of computation that you're going to need to do as you're making the molecule bigger. So that's kind of how quantum computers, all the basic idea came along. It was Feynman in 1980. In the 1980s, like they were realizing that like there was no good classical algorithm to simulate quantum mechanics. And then why not use quantum mechanics itself to simulate other quantum systems like molecules and materials? And one of the first applications, so say factoring, you may have heard about that. Factoring is a form of phase estimation also. So if you want to factor large numbers and break RSA on a quantum computer, then it would be an algorithm which is similar to this one. But you would need many hundreds of qubits to like represent the large number that you want to factor. But factoring is not a very promising economical applications if you want to make money. And just blow up banks. Then one of the main applications that came along was the Feynman's idea, so simulating, say, quantum chemistry on a quantum computer. And the function that you want to optimize, so this is called a Hamiltonian. Hamiltonian is like the energy function of a molecule. So it gives you the description of a material, it gives you the description of a molecule, of like fundamental particles, whatever you want, in such a way that we can easily do calculations. And these, they're called annihilation and creation operators. So if you have like the levels in an atom, like these things will just put an electron or remove an electron out of there. And like there's some energy, so like you can have electrons interacting. And this thing is extremely hard to solve. Like to optimize this function is extremely hard on a classical computer. It would amount to solving all of chemistry. And we can simulate exactly chemistry now with maybe a few tens of electrons and particles. So if we want to simulate quantum mechanically proteins with millions of atoms, right now it's impossible on classical computers. And on quantum computers, it's expected that we can do it. So there's a procedure where we transform, when we take this function, we transform it such that it can be read by a quantum computer, and there's some transformation. And then we can apply the phase estimation. We start with some state, we apply it with the phase estimation algorithm, and we're measuring like energy, and we repeat until we get a low energy, the lowest energy, and then we just say, this is the low energy of my molecule. And it's a trick that quantum mechanics allows us to do. But it's very complicated in the sense that there's a lot of noise in current machines. So if you try to do like the phase estimation, so you try to get the energy of a molecule, you will get if there's a little bit of noise in your quantum computer, it will just start flipping bits around and you won't see anything. You will just see noise and random outputs. And a way to mitigate this problem is that instead of, that came around 2014, instead of trying to do like those logical gates, let's just assume that like we have like controls on the quantum computer. We make those controls variational, so we just allow it's like a digital analog machine. If you want, we just like tune those parameters in some kind of circuit. So we have like quantum gates, they're like a parametrization of quantum gates, and like which I denote like this with like the vector on the parameters, and this like denotes like a sequence of gates on a quantum computer which are parametrized by some theta, like 1, 2, 3. And I will also use the notation with the like the colon here, like n to 1. It's going to come useful later to represent like this chain. And like what is a gate specifically? It's a rotation of an Hamiltonian, also an Hamiltonian again. So like there's this generator here, which is like a self-adjoint, and it's like, say on the block sphere, it's like the vector of rotation around which the state will evolve. So if you evolve it with some, usually like this parameter here is time, so around this axis, then the state will just evolve around this axis. And this allows us to parametrize gates. So we pick an axis, so this is the little h, and we turn the state by some angle theta. And then we have a parametrized quantum circuit. And what this allows us to do is that instead of trying to solve this with phase estimation, we start with a guess, and then we tune we tune the gate, like the operation to some value. We measure the value of this function at the end of the quantum computer, and then we do a gradient descent on the parameters that prepares some state to minimize this function, and we keep repeating until we reach like the minimum value, and then we know that we have the lowest energy state, say, of a molecule of our material at the end of the quantum computer. And even if there's a bit of noise or systematic error, the variational procedure will just like take into account this noise and errors and like reduce the noise. So like these have proven like to work better than like direct algorithm with gates. Yes.
Clarification question. So what's your ground truth? Is it the energy in your molecules?
You don't know it a priori. So like that's kind of the thing with quantum computers. Often you can do an optimization, solve an optimization problem, but you don't have an efficient way to verify that it's actually the solution. Like you can try to measure it. If you have a molecule, you can try to measure the energy. And you can see if it matches the simulation that you're doing, but there's no efficient classical way to verify that it was the right answer other than the measurements.
When you say gradient descent, you're comparing with the simulation?
With the previous results. So say you want a simple case. You want like you have a spin in a magnetic field, and like the spin, like its lowest energy is when it's aligned with the magnetic field. So if you have like an angle of the spin and you're trying to find where its energy is minimum, then you just tune it, like you turn it around, and then you see that like its energy is going down when you're aligning it with the field, and when it's aligned, then you have the minimum energy, and that's it. It's kind of the principle.
So the lowest energies mean local minimum, local optimum.
Ideally, we're looking for the global one. It's not always well defined. In some sense, so some molecules are very clean, like they're stable, and like the ground state, like the minimum energy is very clean. There's some other materials, like if you pick a glass, like glass doesn't have a fixed lowest energy. It's always like fluctuating because there's many states which have low energy, and there's local minima, and they almost all have the same value. So in this case, like you can get fluctuations, and you can get a local minimum. So it really depends on the case. Some molecules and materials have a fixed, clear, low energy state. Some just don't. It's like general optimization problem.
So how do you make a measurement in practice?
In practice, it's a click if you want. So it's like photons in quantum mechanics. So if you have a beam of light, and you reduce the intensity to a detector, you're getting a clear signal. And at some point, when you get close to just the vacuum, then your detector will just instead of seeing a continuous signal, you will see peaks, which means that you have like a exchange of like quantized energy packets. So that's how quantum mechanics works. So like you have say your qubit will exchange energy with the detector, and you will get a click, discrete click, and that's it.
Okay, you mentioned that if once you make a measurement, it's either spin up or spin down.
Yeah.
So there is no way the optimal, the local or the global optimum is somewhere in between.
It's a bit tricky. So okay, you get clicks. So you will get samples if you want, of these clicks. It's going to be like a list of events, and then you will evaluate this function based on these many samples. So it's not going to be a single answer which tells you, and at the end you don't know what is the ground state. You just know you have the ground state, and you know its energy. Because in general, a state like in quantum mechanics, you can have like all possible states of maybe you can, like say if you have 3 qubits, you can have like all possible states, 0, like all possible configurations. 1, 2, 3, 2, 1, 0, 0, 1, 1, 1. 1, 2, 3, right, yeah. So like with 3 qubits, you can have like all these states. But since the quantum computer can be in a superposition of all these, then in general you will need, if you have n bits, then you will need 2 to the n coefficients to represent like the full state, because it can be in the full superposition of all these things. So what it means is that like once you have prepared a state, you have samples, you estimate the energy, but you cannot extract what's the state, because the full superposition, say if there's 1,000 bits, then it would require 2 to the 1,000 numbers, and there's not enough paper in the universe to like write that number.
If I'm just understanding correctly, to simplify, if you have like 2 dice, and you're trying to sample a distribution of the sum, you know that the distribution spikes at 7. But each sample you get is just 2 dice values. So you sample it many times and you construct your distribution to get the underlying information. So that's why each individual state is just one sample of the distribution that you construct.
Yeah. It's like that, and like the further step is that like quantum distribution cannot be sampled efficiently classically. So you can prepare the distribution, like it will be specified by a polynomial number of parameters, so these are the gates. But if you want to draw samples from it, you would need an exponential amount of time to compute what's the distribution and then draw samples from it. While the quantum computer just like outputs the value out of the distribution. In some sense, like the LHC is also like doing quantum sampling, but at much higher energy in a much more complex setting. So it's like firing protons, and then you see all the channels of the particles flashing up. We cannot predict in advance what are going to be like the patterns, but we can reconstruct the structure just from like the description of the system. Yeah, so that's for parametrized circuit, and parametrized circuits are important for QGAN. So you parametrize a polynomial number of gates, you sample, and you optimize the function, and then you repeat until you reach a minimum. And that's the basic principle. And like applications of these, like people are thinking about trying to simulate ITC superconductors with quantum computers, because we still haven't figured out exactly why. So some copper oxide material becomes superconducting at liquid nitrogen temperature. It has like a weird behavior which is not like normal superconductors, and these are very complicated. So if we can do like a few tens of atoms on classical computers, like here there's like hundreds of electrons involved. We can also do nuclear physics, there's a lot of going on here. We can go to more complicated theory like chromodynamics and these things. Yeah, and now QGANs. So like we have these the variational circuits.
Sorry, I'm going to interrupt there. Is there anyone that is confused about what's going on here?
Ask questions.
Right, ask questions.
No, it's. I'm gonna look up how I'm gonna sample from the solution.
Alex.
Yeah. So, question.
Yeah.
The thing you mentioned with gradient descent. So, I didn't get into like conclusion. Do you just so do you like manually calculate the derivatives to change the parameters? So you kind of like slightly change and then calculate, or is that part of that quantum circuit?
We can do it like that. So like with finite differences. Or we can do directly measure the gradients on the quantum computer, and I'll show like how to do that. Like I don't do the full derivation, but I'll show how to do that. In principle, like you can use the quantum computer to get its gradient itself. So if you want like the gradient with respect to one parameter, then you will sample directly the gradient out of the quantum computer. And yes, so like the main topic, I guess, QGANs. It's something we did very recently. Like maybe it's a bit small to read, but like the papers are online. Like you can look at the reference. We started that in late March. Then we wrote that in April, and we are working with Seth Lloyd from MIT who's also advising the company. And he was having the same idea at the same time. We just coordinated and like released the paper like the same day. So we worked it from a more general perspective of quantum adversarial learning. And we did with Nathan a more concrete, more practical implementation. So classical GANs, usually like it's, I guess if you guys are all in machine learning, like you know how it works. So you have some real data and you want to produce, like train a network that will reproduce this real data without having an explicit function to train this guy. So how we do it is that we use a discriminator, and the discriminator will just say whether is also a network which is trained to determine whether some datum comes from the real source of the generated source. And as this guy is being trained to distinguish those two, this one has an incentive to try to reproduce like the original source, and that's the basic principle of adversarial learning. So you have these two here are trying to optimize the same function but in different directions. And for quantum GANs, it's essentially the same thing. The basic principle of training adversarial quantum training is the same. So we have some real source of quantum data. We have a quantum circuit that we want to optimize such that it reproduces the original guy, and we have also a discriminator whose job is to determine whether the samples are coming from the real data source or the quantum system. And there's something which I will use, I use a lot of the density matrices. In quantum mechanics, a density matrix. So if you have those are states, if you want. A state is just a configuration, one possible configuration of your system. So you can have a superposition of two states. So you can have say 0, 0, 0 plus. Those are normalized. Say 1, 1, 1. But you can also have classical superposition. So if you don't know, if you have some kind of bag, it contains states. Say the state with probability 1, it contains state 1. With probability 2, it contains state 2. If these are classical probabilities, then we can represent them with what we call a density matrix. So this object is the generalization of a quantum distribution. It is a quantum distribution. It can represent classical and quantum distributions. It is the most general physical way we have of representing distributions. It's just a very convenient object that we're using for the calculation. So when you see that, it's just a distribution.
So essentially those states of 0, 0, 0 and 1, 1, 1, you can imagine them as vectors?
Yep.
And a density matrix is a 2D representation of those vectors if you can show them as vectors.
Yeah, there's really two parts. There's this part where you can have superposition of the states themselves. So it's really like a direction in the vector, like if those are all orthogonal vectors. And this is really like a classical probability of like having those vectors. So it's the difference between the two.
So what about other 6 states? Because you're going to have 2 states.
Oh, it's just an example. Like this is an example of a classical superposition. So it means that if you were to measure this system, all your qubits would either be 0 or all 1. But nothing in between. While if you have like a classical superposition like that, it more represents, like you cannot, but this guy you can undo if you want, but like these classical uncertainty you cannot undo. That's kind of the difference if you want. How to explain that? Yeah, so like one example is the Hadamard gate. The Hadamard gate will give you a superposition of 0 and 1, 0 plus 1, like that. So like we usually we name this state plus, but if you apply it twice, like it's possible to do the math, then you recover the initial state. So you can undo it, even if when you measure that you have 0 and 1 with 50% chance probability. But if you have a density matrix, which we denote 1/2 0 0 plus 1/2 1 1, then in a form like that, it's really like a coin flip. You cannot undo it and come back to a state with a definite, say, value here. So this is quantum superposition, and this is classical uncertainty.
So like you range from maybe 1,000 times, you want to calculate the possibility of falling 75, 25.
Yeah. So, and this is the most general representation, because with this form, like the density matrix, you can represent quantum and classical superposition. So that's something useful to, well, that's very useful to have.
One question.
Yes.
Why is the normalization 1 over square root?
You just want, what you want is that when you take, like these are vectors, but you can take, there's a bilinear product. So you can take like the an inner product with some other value, with some other state, and you want the inner product to be normalized to 1 such that they represent the probabilities. So this is Born's rule. So you have like a state vector, like it has an amplitude, and you recover probabilities by taking the conjugate, the product with its conjugate value. So say you have the state, say you have the state 0, well, okay, let's use this guy. So this is the state plus. Say there exists something else which is called the state minus. And this is simply like a Hadamard, and 1 gives you like the state minus here. And if you want, say, the probability of obtaining 0, then it would be 0 plus like that, and then you square it. No, there's not even a square. So it's just like this guy here, which in this case, oh, you have to take a square. You need a square, which in this case will give you 1/2. And it comes from the fact that 0, 0 is 1, and 0, 1, they are orthogonal, so it gives you 0. So when you take this 0 with this one, gives you 1. This 0 with this one, it cancels, it gives you 0. And then with the square, it gives you 1/2. And it means that if you have plus and you want to know what's the probability of measuring 0, then you have the 1/2 chance of measuring 0.
Okay. And so the normalization is just the square root of half.
Yep. And so in this case, if you have a row like is a bilinear form. So like if you want the probability with a row, you would like put the vectors on both sides here, but then you don't need a square. So in this case, if you have this, you want to know what's the probability of 0, then you put zeros here, you get like 1/2. And like if you put the zeros here, then like these become 0 and you only add 1/2. So you have 1/2 of chance of measuring.
It's not always square root though, because like those coefficients can in principle be complex.
Yep.
Imaginary and real, that's why you have the modulus square to get the problem.
Okay, so like when it's -1, you would get like, if you
What is minus?
if if you want to square root minus 1, let's say if it was minus half, the square root minus half is going to be I divided by square root.
Exactly.
Complex, yeah.
Or you can have like states say 0 plus I like square root of and then like normalize like that. You can have a phase. So it means like on the sphere, like the phase here describes like the position on the equator. So you have one angle that tells you if you're like the latitude, and the other one is actually longitude. And yes, and yeah. So like if we have sources of data, say they're labeled data, we can label. We have some like a set of n qubits. We have like a bunch of qubits which just like give us the label, like it's just a binary value that represents like a label. And we can have some, I call that like a bat, it's just like workspace if you want. And like this can come from VQE. Say we're doing like a VQE. So like chemistry, we're optimizing circuits for molecules. We have like a long list of molecules, optimized molecules, and we want to generate new molecules. Then the list that we have of optimized materials and molecules could be this guy here. So like we know how to generate those on a quantum computer, and we want to build like a generator that will also mimic this distribution of known molecules. Something like that, and they're labeled. So you can have like drug molecules, non-drug molecules, and you want to generate say new drug molecules or something like that. They can be labeled.
So what is out R? Label R?
These are like the name of registers that I use. I'm not sure if it makes things clearer, but it's just like so this is like the register where you output like the distribution. This is the register where you have the label, and this is the register where you have like the workspace. Just to keep track, because the further like the circuit gets a bit more complex. And like this operation, like it acts on these things here, and it returns a real distribution. So these density matrices. And for the generator is a parametrized circuit, because we don't know how to parametrize a circuit that will reproduce all those gates here. And we also allow it to have like a noise source, like for classical GANs, but it's not really necessary in quantum mechanics, but I won't go to those details. And again, we get like a distribution. And we have like, we can do also a discriminator. Discriminator is also a parametrized circuit which take as input some register which puts the answer, like a real or fake, and that we can measure. So it's like we can put a spin there. If it's up, it's a real distribution. If it's down, it's a fake distribution. It can have a workspace. It takes also into input the label, because it must know what label it came from, and it takes as input the distribution that's coming from the circuit, from the source circuit. And then the discriminator takes all those things, and for some parameters, it will tell you whether this guy came from a real source or a generated source. And then we can reconstruct like the cost function of adversarial learning. So it's a min-max problem. So we want to maximize, we want to maximize the probability that the discriminator given real as input identifies real, and the discriminator given generated sample like outputs fake. So and this is like the cost function that we want to optimize. The discriminator wants to maximize this, so it wants to maximize like its success. But the generator is trying to fool the discriminator by creating the same distribution, so it wants to minimize this function. So it wants to minimize the probability that D will assign a fake label when it's the generator which is feeding it data. But for calculations, this is not a super useful form, so now I'll push you a bit more formalism. I guess if quantum computing like gets real, you'll probably like see these things a few times and it make like dig in, but like the first time, I guess it's very, very dry to see.
So out, is that out bar /G UFG, what is that?
So this is the register where like if you have a real source, it outputs the real source, like the distribution of the real source. And if it's the generated the source, then it's the channel where you put the distribution of the generator or the real data.
I see.
Yeah.
Okay. So you have. So isn't the lower part the generator?
This is where you put the real data or the generated data. It's probably two sides further down. It's going to be a bit clearer, but it's just a compact notation for where like you would have this circuit. Either like you feed it like a real data when you only have R, and it's outputting the distribution of R, and this guy has to determine whether it's real or fake, or you have the generator, and this guy again has to determine whether it's a G or R. So usually like you have what we describe as an initial state. So the initial distribution is what we decide for the quantum computer. We have like zeros here, like we have zeros here. We have like labels which we denote with tensor products. So the tensor product just means the distribution when it's independent of each channel. So it's this symbol here. So like we have the zeros which are independent of this guy, which we have zeros again, and like so this is the notation to describe the initial distribution. And then when we have rounds of training, we either feed it real data or generated data, and this is where like I split the two. So in the case where we have a real source here, when we work with quantum registers, you usually have to define the operation on the full quantum computer. So like it's going to be a unitary reversible operation where we do nothing on the first part. So when we do nothing, it's identity, and we do R on this part here. And then when we evolve a state, it's always going to be a gate. So we have some state prime. It's going to be the evolution times the initial state, and then the reverse of the transformation. It's just to keep track of all the numbers. That's how evolution is defined quantum mechanically. So you take a distribution, you sandwich it between the gates. And here at this point we have the real distribution, and here we have the generated distribution with the same principle. So we do nothing here, so identity, and we do a generator here on these channels, and then the distribution on this line here will be this evolution of the initial state with the generator operation. Yes? No? Well, almost there. And finally, like how do we describe the discriminator operation? Again, so it's the discriminator acting on these channels here and not on those. So there's the like acting nothing here. And again, we take the real distribution, the real distribution or the generated distribution here, and we sandwich it between the gates of the generator, which is the same here on both cases. And we come up with an expression which is like the form, it's linear in the state, and it's the form of cost function which we can optimize on a quantum computer. So this is, here. So this is the form we can have. And this is also something for which we can take the gradient. So this is like, once we have this function, then we can do adversarial learning on it. And it's going to be amenable to gradient descent. So we can have like the parameter of like the discriminator at time, like at step k, which will be updated by some, by the gradients normalized by some learning rate chi here. And this gives us like the next parameters for like the discriminator, and same thing for the generator, but with the minus sign because we're going the opposite direction. And then the training really like proceeds like for classical GAN. Yes.
So can you explain this cost function a little more?
So like there's just going to be a constant term that it just comes out of the equation, and then there's something which is called a trace. So a trace is like that's how you denote the expectation value of a quantum variable. So if you have, if you want like the expectation value of some function, and you have a distribution rho, then we note it with the trace. It's going to be like rho, which is a matrix, and the operator is also a matrix, and the trace is the sum of the diagonal elements. And this will give us like, this is like trace is what it gives us an expectation value.
Expectation value is the average value?
Yeah, any statistics.
Statistically. So what is Z here?
Z is the Z that defined it's the no, it's an operator, like the capital small z is noise, but capital Z it's the operator real real minus fake, which means that if I give it something which it recognizes as real, it will. So if I give it like a real, if I give it like a real source, the discriminator here will, like if real is at the top of the block sphere, it will try to like optimize its parameter to output like this value real, and if we give it a generator, then it will try to output fake. So it's just like you can view that as like the orientation see on the sphere. So there's the like the sphere. You can just like label the 0 as real and 1 as fake. Just a bit. It's a bit value.
And why is it rho dr minus rho dg?
So here it's gonna be so like the trace is linear. So the trace of this is just like the difference of the two traces of here this is the distribution at the output of the discriminator.
I see.
And you're evaluating the expectation value of like this real or fake thing, and you want the opposite. So you want to maximize say that the discriminator returns that the generator is like identifies the generator as fake, and this z is just like this thing here. So it's really
your goal here is to get these two row distributions as close as possible.
Yes. Yes. And it's linear in those distributions, and so it means that from a computer, a quantum computer, here we would get zeros or ones, so real or fakes, and we would try to and then we try to maximize, say this function for the discriminator and minimize it when it's the generator. And that's the algorithm. So we start with some initial guess for discriminator generator. We flip a coin whether we train, we put a real source of or a fake source. Then we have some heuristic, and we can train G or the discriminator. We update the parameters. If it's converged, we go back. If it's not converged, we keep going. If it's converged, we stop, and then we have reached the end of the training. And there's a way to do gradients directly on the device. So, if you have like a chain of gates, of parameterized gates, then there is a direct expression that tells you that if you take the derivative with this parameter, then it's going to be the original gate. So some gate here times the generator itself. So like if you here is generated by some angle, so h is this angle, and like theta is how the vector goes around this angle. Then you get this equation which tells you how this will change when you change theta, and like this is actually Schrodinger's equation. If you look at Schrodinger's equation, it's this quantity here, and you replace the theta by time, and it's Schrodinger's equation. And if the gate is in the middle of a sequence, it's possible to, like this expression, like for the full sequence, will give us, will mean that we put h just before like the gate that we want to derive. And here there's some more notations for those who want to look at the slides, but just to make it consistent. So if you have some quantity p, so like or h, which is a statistics, and you have a list of gates here, like the expectation value as a function of the parameters will be like this whole evolution, and then we measure p with the expectation value of p, and then like if we do the algebra, we can also take the derivative. So how does this change when we change parameters theta j? Then it will give us some kind of expression which like justify the whole notation if you follow the slides carefully. But it also gives us an explicit circuit. So we have like the original gate here, so 1 to n, which I represent with the colons. It means that we do a control operation. So we put a qubit in superposition. We do a control operation, of the Hamiltonian, then the control of the operator, and what we measure directly at the output is going to be the gradients. So it's kind of like quantum mechanic magics. If you try to do this derivation in your head, it's not obvious. But yeah, so it means that if you have a parameterized quantum circuit, there exists a direct circuit in quantum mechanics which gives you directly the gradients, which you can use to train these models in quantum machine learning. And just a quick aside, since we have like the derivative of a circuit, we can also take the derivative of a derivative, and we can even measure like the Hessian matrix directly on the quantum computer, or like any higher order derivative of any function using a method like that. And like if you like take the full expression, like don't try to read that, but like if you take the full expression of each derivative, so like we get the gradient of the generator, it means that for each gate in the generator, you just put like a control operation and you can measure those gradients. Same for the discriminator when we have a real source, and same for the discriminator when we have the generator source here. And these are the functions that it is computing. If you try to evaluate that on a classical computer, you would get an exponential overhead just because you're trying to fully simulate quantum mechanics. And we tried on a simplest possible numerical example. So we have like a real source for like when it's labeled A, it outputs 0, and when it's labeled B, it outputs 1. So it's like a control NOT if you want. So it just flips. So if we start with 0, 0, it just flips the bit when this one is 1. So if A is 0 and B is 1, just to A is 0 and B is 1, just to make it a bit clearer. So what we want is that we want to train a generator so that it can recover this this little function here. And so we need to parametrize a quantum circuit. So like this looks nasty, but what this is, it means that we parametrize it by a sequence of layers. The first element is going to be X rotation. So you have your block sphere. The first one is an arbitrary rotation around the X axis for each qubit. Then you have an arbitrary rotation of Z around each qubit. And then there's a 2-qubit ZZ interaction. I'll show it just after. Between all pairs, between all nearest neighbor pairs, and then we repeat this layer. And this layer is universal for quantum computing. So if you have enough of them, then you can, in principle, rewrite all quantum algorithms, polynomial quantum algorithms using like a sequence like that. And like just back to the block sphere, so like a single qubit rotation, it's like a rotation around this axis on the sphere, like a X rotation. Like if there's the X axis, it's a rotation around this axis. So it's like the first part of the ansatz. And then there's the 2-qubit rotation. So ZZ interaction, it means that if you have like a spin up, like the second one, it will turn like say clockwise. But if you flip it, then this one will turn anti-clockwise. So the ZZ interaction couples the motion of like two neighboring spins. And it's possible to build a C0 using this interaction and like this sequence here of with a ZZ in the middle. So you do some, there's going to be first a rotation of one of the qubits, then there's the ZZ interaction, and then ZZ interaction, and then finally you return everything, and it's possible to build a C0. And this is the solution, and this solution is actually allowed by our ansatz, so it's like X, Z, and ZZ rotations. So the circuit should be, like the algorithm should be able to find and identify this one just by construction. And it does, well, okay, so like on what we parameterize, so if like the green box are the little X and the Z are the little blue and the ZZ are the little black one, this is exactly what we parameterize on the quantum computer to recover like to have G reproduce this, and we get and it works. So like if this is the cost function here, you see that after a bunch of training steps, it does go to the point where the probability that D discriminate G or R is like 1/2, so it's like flipping a coin. Well, eventually, like its fixed point seems to be the case where it just identifies everything as real. I don't exactly know why. And these are, it's just like the individual cost functions. So this is the total one. This is when we put the real source, and this is when the yellow one is when we put a generated source. But I won't go over the performance.
I have a question.
Yes.
Can we apply, just want to know your thoughts about it. Can we apply early stopping in this velocities, like before it goes constant? Can we apply an eavesdropping algorithm?
And I'm not an expert in quantum and machine learning, so which one?
So I'm talking about machine learning, where you get to a stage that you're going constant, so you stop at that process and you don't go any further.
Ah, yes, you can. Yes, in principle, like all the like from the Goodfellow paper, and like there was a follow-up where like it just improved methods for training GANs, and all the methods applied. They're easy to define. We didn't go through all of them because it's long, but all those methods in principle they apply. There may even be a way to use dropout. So if you remove gates at some point, like maybe there's many methods, but we haven't tried them all yet. And you can also define like the measure of cross entropy to see for the quantum mechanics mechanical case. So this is the exact representation. It's very similar to the classical case, and it goes down like as you're training, which shows that like both distributions end up being the same. But you'll never like on the quantum computer. What you're measuring is this. You cannot measure this efficiently on a quantum computer. You cannot measure entropy of a state or cross entropy efficiently. And that's it. So that's kind of the initial like idea. It came from like the advances in quantum chemistry on quantum computers. Say you have like a large database, and you want to generate new materials from from this database. Then using a quantum GANs in principle, you can train the distribution that will generalize this like the original data, the quantum data that you have, and produce new types of materials one day. That's it.